Welcome to Ask and Learn.
In this problem, again, we're doing everything symbolically. So we have no numerical values, but we're told that writing the first and second law relations and simplifying, obtain the reversible work relation for a uniform flow system that exchanges heat with the surrounding media at T naught in the amount of Q naught, as well as a heat reservoir at TR in the amount of QR. And again, we want to eliminate Q naught from the system, from the two equations that we have. So we have conservation of energy, entropy equalities. So energy in minus energy out is the change in energy in the system. And likewise, the entropy in minus the entropy out plus the entropy generated is the change in entropy in the system. So plugging in everything here and doing some rearranging, we have that we have basically everything that we had like in the previous problem. We have all the energy flowing in minus the energy flowing out. The heat transfer flowing in, again, these are positive in. And then we have minus the change in internal energy in the system. So we have this term here now. And so what we have is, and this is inside the control volume, okay? So all this stuff is flowing going across the control volume, and this is inside the control volume. Likewise, entropy is very much similar to what we had in the previous problem, except now we have a change in entropy in the system, in the control volume here. So this thing here. So again, we have the entropy generated, and we have the entropy flowing in, entropy flowing out, and then the entropy, the entropy flowing out, the entropy flowing in, the entropy flowing in from the heat, and then the change in entropy inside, since it's not a, it is, for a, it's uniform flow system, but it's not steady. So again, now to get the useful work, we need to subtract off, to get the, what did I do here? I think I put a U here where I should not have put a U. To get the work, okay, so then what they ask us to do is basically eliminate Q naught. So we can use this equation to solve for Q naught and plug it in here. And we wind up with this lengthy monstrosity here. But in the end, this is kind of like the exergy in minus the exergy out, and then some, the kind of the reduction from the heat, or from the temperature here, okay, and then the change in exergy kind of in the structure in the system. So again, you can think of these as exergies if you want, or kind of an exergy flow or an exergy in and exergy out, or the change in exergy inside. When I learned thermodynamics, we didn't talk about exergies, so that's not how I really think about these things. But again, it's best to kind of just whatever your intuition, kind of in the best way for your brain to kind of wrap things around and develop an intuition for these things. So my intuition basically says that, well, we're this energy, this entropy like stuff flowing in, okay, is taking away from what we're putting in, and then this entropy like stuff that's flowing out is taking away from the energy stuff that's flowing out. Okay, that's how I think. And then we basically have this term here, which is always hampering us. So if we are trying to, if W is negative, this makes it more negative. But in the end, if W is negative, that means we're putting work into the system, and we want to minimize the magnitude. And so whenever we take the magnitude of this thing, so we take the magnitude of this work, this thing is always going to hurt us. And then likewise here, we're kind of taking away some of the internal energy that we could have maybe extracted from this here. Again, it's kind of how you want to think about it. You can just think about all these terms. Now, what then we need to talk about the usable work. So we need to subtract off the work that we did on the surroundings. Um, so again, this is not a constant volume process, or this term would be 0. So we weren't told that it was or that it wasn't. Let's see here. Now we can, to get the reversible work, we just take the usable work and set the entropy generation to 0. And so again, we can think about these as kind of, again, if you want to think about it in terms of exergy-like things, again, all we really have now is that, this term is there now. So, in the previous cases, we didn't have, in the previous problem, we didn't have this stuff here because we had nothing. It was steady flow, so there was nothing, no rate of no energy change inside the control volume. There was, or there was none of this either. But I think in the previous problem, did we have? Yeah, we didn't have any of that. But in 2 problems ago, we did, because this was, again, this last problem is kind of a combination of this problem and this problem. You can kind of see we're adding all more and more terms here. So if we look at the irreversibility, or the second law efficiency, we take this divided by this, and you can see if we did that and we kind of expanded it out a little bit, this term here and these terms here that I'm circling would cancel out with these terms here, right? So if we expanded the fraction, and so that would give us a 1, and then we'd get minus this over this. So that's kind of, basically the, if this were 0, then we'd have a second law efficiency of 100%. But because we have this term, but we need to divide it by this guy, the reversible work that we could have possibly gotten out, and that would be now that would be the second law efficiency. 1 minus this divided by this.